if I take, if that's 2.5 milli, that is 2.5 milliseconds. When this amount of time has elapsed, 2.5 milliseconds, this is equal to e to the minus 1. Okay? Now, do you have e on your calculator, the letter e, the rational number e? See, I don't even have it on this. This calculator is so old. I get 1/2.71828, okay? Or what's the inverse of that? .367. So in 2.5 milliseconds, this curve has gone from nothing to about 37% of its maximum. All right? So that's one time constant. So if you go 5 of those, 5 time constants, you are going to hit a point where this curve effectively reaches its maximum value. So take 5 times 2.5, what do you get? 12.5. So you actually measured on your computer, remember that you put those two cursors, you measured 10.3, you calculated 12.5, and so you're close. All right? And I guess when you weren't here, we were going over that whole concept. And if you look at, so this number e it's an irrational number like pi. .718281828. That number appears in every one of these equations. And for voltage, it takes 5 time constants, 5 times this ratio here, for the voltage to go from 0 to maximum, and for the current to go from maximum to 0. You've got that same, you've got a different formula, but that same relationship in terms of time constant. For an inductor, you switch voltage and current, and you have the same thing going on. So that's what that's the whole idea. So I just wanted to give you a feel for that concept of time constants. Okay. Okay, who has questions? I'm going to have to fix that one up. Okay, I'm going to jump right into another lab, and then once we're done with this, we're actually pretty well done with chapter 11 on inductors. So this particular lab, same kind of deal. I'm going to have you build a circuit, but it's a little bit more complex. It's going to be a resistor and a capacitor in series, and a resistor and an inductor in series. And we're going to be using a 4-trace multisim. So one trace is going to be on the inductor part, another trace on the capacitor part. You're going to get multiple waveforms on the screen. I want you to see how the voltages and currents how the voltages interact for the inductor and the capacitor. Hopefully I got the values squared away and this will work. All right. So try that. See what happens. I'm getting fancy on these multi-sim circuits. You can see when you get your paper that I have the wires colored with different colors. You click on, if you right click on a wire, you can change the color of the wire. That might help you with your, it might help you trace out your circuit better. Whatever color you make the wire, that's what the color is for the waveform on the screen. Okay? Oh, you're getting closer.
Pretty good, like, it's like it's natural, you know? Who are you? Don't forget those steps. What are you talking about? The positive and negative steps. Oh, yeah.
seeing anything?
I guess.
Whoa. Something.
Must have to do that.
Uh-oh, problems.
No, I just wanted to check it with you. Also, I want to ask, I forgot, I didn't hear what you said about changing colors.
If you click on, right-click on a wire, you should get a color chart.
Oh.
Yeah.
And then it'll show them here with the color?
Yeah, whatever color you make the wire, that's what the color of the waveform is.
I should probably just go.
You don't have to. See what you get, man. Yeah, see how those created? Wow. Look at all those
The
colors.
working looks the same right now.
So the green, you got the green and the red, the orange is, what's the orange one?
It's just like sticking around.
Do you have all the adjustments on the 4 channels?
Yeah. Yeah. Dave's 5.
Nick, are you getting waveforms in all 4 channels?
Yeah. Like orange is there, it's just like.
Yeah, but orange should be pronounced. A is 5 volts per division. And, okay, B is, C is 10. D is 100 millivolts. Okay, now we're measuring milliamps because of the clamp scale. Oh, what about the scale on your clamps? 1 millivolt per milliamp. What do I have it? What do I have for the, what do you have for the raw source?
It was just. That's all.
Let's see, here's, well, you got 4 waveforms out. What do I say for the source?
25 hertz.
Okay. Peak output of 5 volts. It says,
Amplitude's 5. What does it say? 5. So maybe the peak for the amplitude? I guess 1.
but you have,
Yeah, I don't know why. It doesn't say 5. It just says 5 volts. But this is like, you know.
VP,
any peak output VP.
So you put 1 BP?
not 5.
Oh, okay.
No, that means any peak output VP
Yeah, yeah.
of 5 volts.
What about the offset?
I think it's the same as the high. Let me check the other one. Well, that offset zero.
Oh, I guess. Try that.
Can you manually set this in? Let's hit him up. Maybe your wiring is on.
Nah, man, it's perfect.
It looks perfect. Look at that. How are you on it? You want it?
Dave, do you have your set to AC or DC?
It's decent.
Okay. Well, they're all AC, so I think we can change them all to AC.
Oh. Something very basically wrong.
I'm guessing it's just metal wire.
Oh, wait a second. Do I don't have anything on the trigger. Get rid of that wire there.
Oh. It's too close.
You wanna connect the ground?
That's why, because it was too close to connect it all.
There you go. Now you got it.
Well, that makes sense.
Oh, yeah, that's good. Wow, look at that. So one of those is voltage and current on the capacitor, and one of those is voltage and current on the, let's see your circuit.
Look at this party right here.
Wow. Yeah, so you're getting, so here's your current probe. Voltage, capacitor.
Why is it that when you call here, it's,
And the voltage across the
I like all the
capacitor.
There's a little more.
It's the red.
You're right.
All right. The voltage across the inductor is the green, and the current through the inductor is the yellow. So that's how you can tell. Okay?
Oh my God, this is fucking bad.
How we doing?
Don't.
Figuring it out?
Let's take a picture of
Not done
it.
wrong. You're done. Let her flicker. There's all kinds of adjustments on this. Control what? What is this? Oh, that's the probe.
So here's the beginning right here. This is the.
Okay, so you have your probe going to the meter. Your capacitor, let's change the color of that guy to blue.
Look at the stem.
So we have kind of- So the blue is the current through the capacitor. The red is the voltage across the capacitor. You get everything connected to ground. The green is the voltage across the inductor. And the yellow is the current through the inductor. That's this guy here, that's just the ground. Okay, so you got everything grounded, good, good, good. How about your values? Okay, good, they are correct. All right, so now let's, we want to adjust these here. Channel A is 5 volts per division, 5 volts per division. Channel B is 100 millivolts.
What's so funny?
Okay, channel C is what, 10 volts per division? Channel D is, okay, that's good. Going DC. Are they on DC for all of them? Yeah, I know.
Listen.
And what about these guys? What's the scale on that?
What did I say?
Feel like it's mayonnaise?
I guess so. Yeah, 10 milliseconds per division. Okay, that's good. Yep. All right, now. No. That's good. Now what about this guy here? We're getting AC, we want that. We want a square wave. What's the value that we, 25 hertz? 5 volts peak, 0 offset, okay, good. That's running. Whoa. So that's it, pretty much it. Let me see the yellow, what's the yellow? The yellow is the current through the inductor, which is D, right? This one, I'm making D higher. Okay, there's, so we can see it better.
What?
What's the red? The red is the voltage across the capacitor, which is A. So let's make that high. A little bit higher.
Oh, wait, what comes out on Suicide Squad?
Russell, what are you getting for the voltage across the capacitor?
I thought it came out.
Did you start your circuit yet?
Really?
It's not running on the I'll get it.
Well, because I hit the square wave.
Oh, it comes in August.
And what's blue? Blue is what? The current through the
Something's coming out soon.
capacitor,
Civil War.
which is B.
I know, something else though.
Civil War.
That looks good.
Rogue One goes out this December. No, you didn't tell me that.
So anyway, yeah, it's curving a little.
Look at my heart.
What is it?
How does yours look? Probably better than mine.
You know, his is bigger though.
It's more recent though.
To get a real
About
job.
about 4 years apart from us.
Forget that.
I kept saying, yeah, I'm gonna make that about 4 years.
I would go ahead and
You're
run
green
that.
because I had an idea.
Oh, I went and saw this, Hardcore Henry.
That's funny, you know?
That's
It was
pretty
honestly
close.
kinda cool.
I still haven't seen CC told me that.
I'm gonna draw it.
Yeah, so you see the yellow?
What did we go to see? Oh, Revenant. That's right.
That's the,
Which two are
that's the
higher?
inductor.
Yellow? Yellow and red.
So do
Yellow,
I.
red, blue, and green.
Okay, so A and C.
It doesn't matter, it's which period.
Yeah, A and
Royce,
C.
are you doing all right?
Together.
The question is,
A and C, and then B and D. A is the number C, and B is the number D.
it's not different.
Listen here.
Yeah, and change the offset to 0.
I don't think it's that.
Good, and then just change that to
A and
Options
C.
are, voltage,
Yeah.
plus
Yeah,
capacity.
run it, see what happens. And it, what?
No,
You haven't
that's
grounded?
Yeah, because these are all the four, these are the four different lines.
And the first,
Voltage across the capacitor, that's blue. Voltage across the inductor, that's green.
What's the front?
The B is on one of the others.
so they're all connected to the alpha.
Orange or red.
I put it as a black instead of yellow.
That's fine.
Yeah, to the first one.
Well, your waveform's gonna be black. You won't see it.
One goes up from really good.
Do you want to see it? Yeah.
Run this
And
convergence.
then I already set these A, B, and C to the.
5 volts,
Mhm.
B, 100 millivolts, C, 10 volt, D, 10 milliseconds, blah, 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 DC. Auto.
It's really quiet.
Converge, see what happens.
Come on,
Something
go
going
for
on
it.
there.
I'm
They'll
gonna
fix
say
it.
it's a luxury, please.
Want the broccoli haircut?
Are you here for it?
Yeah. He said he wanted to rise that broccoli haircut.
Wait, I wonder if that's if the skin has it, because maybe you got skin for ice.
I thought they changed it. I think they changed it to, but they changed it for the skin tone.
Red should be the voltage across the capacitor. Yep, beautiful. That's what I'm saying.
Okay, so rise chicken down.
Which pair away from similar in shape? Yeah. Yeah, yeah.
Matter of fact, if you drop this one, I think it
Let me see, you're getting such good waveforms, I
If you're
don't.
trapped in that, they match.
Yeah, yeah. But your waveforms are so good that, I don't know why.
It's just because of like how they have
Yeah,
that.
did you follow the instructions? What do you have for the trigger?
These are English, so.
Oh, maybe I missed the trigger.
No. Russell, is yours? Yeah, I think you're doing good. That's the best one I've
Yeah,
seen.
there's nothing in there about the trigger.
Yeah, it's still not.
The only one for using SKT skins to improve them and add another.
Yeah, because they were kind of trash out of it. Even Faker said so. They were
This happens every now and then.
With me too, like I realized that's what all
I haven't been
I'm
able to 6 skins for 18, not 5. It says they're making it for easy for me. Because easy for me to really well, everyone calls me the best vehicle ever. Even though the fight will make it fun. Oh, he has to have like he doesn't have a broccoli.
Oh, wait, does he have like a metallic face in it?
No, that's just headphones.
I meant like, but like his face is black. And then like there's a little cut off the
That's blue with glasses.
Who's it called? Silver?
simulation never fixed.
I thought it would be so. That was right. I thought it was a revolution. A long revolution. But I was sure I'd get that. I'd get that every single thing.
Oh, it's not too
Oh, we actually had a date to these. The second gone. I think it's on for a little bit.
It'll change something.
versus something.
The two days.
That's the original. Oh, yeah, yeah. What was, what about, remember the game where they had with Gangplank? Yeah, but up to the minute.
Okay.
Yeah, what was that even called? Like white markers? That was in
All right, so, close it.
And then there was the Duvall.
Whatever. Stop going there.
Irvy's one.
So you got it.
When you put your the little emblem on it.
What's the white one? Is that the one where you had the wire, the black wire really turned out, or the white wire?
There's like a hard one.
The black wire turned out white, that's
Yeah, remember they did
interesting.
it automatically.
Yeah.
That was Irv for high school.
So the,
There might be both actually.
here's the key to this, those are good waveforms.
That's just because they-
The,
No, the last one.
red
was
is-
difficult.
so the voltage across the capacitor is the same shape as the current through the inductor. See that? And
Here's one.
Brother?
current through the capacitor with the blue is the same shape as the voltage across the inductor. See how they're kind of dual, opposite, voltage and current, yeah, those are good, good. I'm just gonna put a shoulder out. You're doing okay, there's something. Nick, are you doing all right? Makes sense, okay, you got all that, good. Which is that way for your symbol. Current through the capacitor, voltage across the inductor. Yep, those two. Okay, good.
See this last video tonight, or?
No.
Yeah, I feel like there's
I got a couple. You have to go?
Oh, yeah, yeah.
Not really. Okay, not too much
One,
longer,
two, three,
another,
four, five, six,
half hour.
7, 8, 9, 10.
Well, I have this, this, I think that was the only thing in that stack.
I wanna make sure.
Might have one more, I'm not sure.
That's pretty much the same thing.
I know.
You said it was snap and it's like overlaid on like much.
I wanna make sure that this is, that like the question, cause we were like, how's it being asked, for what they were like.
yeah, the voltage across the capacitor should be the same, should be similar to the current through the inductor. So A,
Oh.
D, B, and C, those shapes should be the same.
It's 7 hours, not even close.
So you look like?
Yeah, I was wondering how the question was being asked, but I said that the answer wrong.
Sounds like great.
Once we get past 2 wires, I don't know what I'm looking at.
Yeah. The number of the numeric system.
No? That was a 7?
Wait, what did you answer?
What do you have?
Mr. Cook,
I'm not gonna
do you have the intro to the chapter 8 homework? Like what questions and stuff?
A, B, C.
Chapter 8,
I figured.
Yeah.
I
Well, at least I got one
do,
I know.
It is clean, that's on
chapter 8's on web.
You'll never know.
Let me see here.
I got 6 trophies.
Do you have mine in there?
You don't know your names.
Oh, no. Beluga?
Corgus.
Graggies?
Corgus. You know what's funny?
Yeah.
You didn't watch all
Taking
this.
our drops.
See everything?
20 minutes.
It's a holiday, you know, like, people really, I found it a holiday, because I've been for couples of years in Africa. But it's like, holiday, kind of the same, I don't say look. There's also a bunch of houses in China. There's one day, there's Monday. They're kind of like Valentine's.
Yeah, they got the more for too, no?
Did you see South Korea's even much better? Look here is fancy, South Korea's not so much a big giant Mexican over the border.
Hey, I heard the border bills are scary.
You like, did you draw?
But there's
the
one
border
thing
in
that
the
big
paper?
companies
Yeah.
that
You drew from the drawings?
Yeah, I don't know if that's true. I did. That's an act right there. It's an act.
they're so mad. And
I found
I think North Korea's
the homework.
You found it?
Yeah, it was on
weapons
the,
drill on Blackboard.
It is on Blackboard, that's what I was gonna look at.
The biggest weapon test in history.
Just like
July ammo of the Drop Mountains. That's They have so much fun.
military sabotage. Take up.
When I was there, they're doing lots of, when I was in the Air Force for a while, we did a trip on and yeah, they was just like coming like, aliens that they're just shooting at crap, like stuffed animals and shit. Just anything that would hang. Just like all this, there's a box of freedom and democracy. Yeah, some of it was even Japanese, which was Japanese stuff, so it was like, all this anime and stuff they're shooting over.
After you were stationed in Korea, don't you get to pick your next base ever?
Oh, I don't know, I was a station, I was at Denver.
Oh, okay.
I flew on cargo aircraft.
Oh, okay.
I hit some
Yeah,
random
those
places.
Because my friends are Air Force, so if you get stationed in Korea,
Yeah,
you get to pick whatever you want.
yeah.
It's like Korea and then somewhere else if you get stationed.
Pretty much anywhere overseas.
Yeah.
I think it was something, I don't know, every time I saw it.
Well, you're in probably Seoul because of South Korea. Yeah, but she's the better one.
This is one of the places I'm going to. Hold up. This is one of the places I'm going to.
The one with the internet.
It's pretty much Disneyland.
You wanted to
There's a
think
thing called Magic Island, and that thing looks exactly like.
Oh, it's the Korean Disneyland. Wow, it actually is. Wait, what's that place called though?
London. It is. And that's like the city of that, so it's. It's Korean Disney.
Oh, look at that.
Look at the castle.
I don't, my dad was in Korea, no. I don't know.
It's like Johnny Volleyball. What's it called? Exact same as Disney. It looks like a newer one. Ah, let me see. Let me see, doesn't it? I don't know what else it is.
How long you say? Oh, 5 weeks, that's a long time.
Yeah, we're leaving, June first.
Like, how are you guys staying in a hotel you're at?
Hopefully. I think my mom got me pregnant. So I don't know. So I guess what happens to you.
Like Korean time.
Why are you going to get egg glass? Why are you getting another? You're not getting nothing.
Ready to go? Okay, one tidbit with, a couple of tidbits with inductors. Do you remember from last week, we talked about capacitors, that when you feed a capacitor with an alternating current, the effect of this phenomenon here, where voltage is zero, current's maximum. Voltage maximum, current is zero. For a simple DC circuit where you just throw the switch and you have that single response, if you extend that concept to alternating current, when you have a circuit with just a capacitor, you have a situation where the current leads the voltage by 90 degrees. And we use this little memory device here to make sure that we remember that relationship. C is the capacitance, I stands for the current. Years ago, I know V is voltage, but years ago it used to be called electromotive force. And so if you just remember the word ice, so for a capacitor, current leads voltage, okay? Well, the same sort of thing is true for an inductor, but it's just the opposite. In an inductor, the voltage leads the current by 90 degrees. Now that's when you have an inductor without a resistor. We were looking at RC circuits where the resistor wants the voltage and the current to maintain the in-phase relationship. And the inductor and the capacitor wants those two parameters to be out of phase by 90 degrees. So you have this tug of war going on. In an RC circuit, voltage and current are out of phase by some angle less than 90 degrees. Well, the same is true in an inductive, an RL circuit. You're going to go over that next week. But in a purely inductive circuit, current or voltage leads current by 90 degrees. And there was a memory thing going on with this as well. Here's the symbol for the inductor. It's the letter L. Here's voltage, here's current. So when I was in school, my professors always said, just remember Eli, the Iceman.
Bless you.
You just remember that sentence? Current leads voltage in or voltage leads current in an inductor. Voltage leads current in an inductor, current leads voltage in a capacitor. Eli, the Iceman. And of course, this is a carryover from the early 1900s when you didn't have refrigerators and the Iceman always delivered ice. Hey, Michael. The Iceman always delivered ice to your door once a week to keep your food cold. And so that's where that came from. Eli, the Iceman. All right? That's tidbit number one. The other tidbit is that as in a capacitor, when you're feeding a capacitor with alternating current, you do have a certain amount of opposition to the flow of current. These things aren't perfect. And so for a capacitor, we called that opposition capacitive reactance, and and I gave you the formula 1/2 frequency times capacitance. And that will tell you the capacitive reactance of a capacitor in an AC circuit. It's measured in ohms. 1/2 times the frequency times the capacitance. And you can use this just like resistance, all right? So it's it would be, instead of resistance, you would have I equals V over XC. Remember that? Okay? And then you have the other two forms of Ohm's law. Well, in an inductive circuit, the inductive reactance is X sub L, and it's equal to 2 pi times the frequency times the inductance. So this is the opposition that an inductor has to the flow of alternating current. It's measured in ohms, and the same rules for Ohm's law apply. Okay, you just replace R in Ohm's law with XL. Okay? So just remember, I mean, if an inductor is, you have a fixed inductor, and usually they are fixed. You can get variable inductors, they're not real common. If you have a certain value of inductance, and as you change the frequency, then the inductive reactance changes. Okay? You remember also we had, I showed you the relationship between, I showed you how a sine wave can be represented by a rotating vector, which we call a phasor. Okay? So when you have well, that's actually next week. That's RL circuits. Just wait for that. Okay, so here's what you want to remember. This guy right here, Eli the Iceman, and this. Once you know that, you can just use Ohm's law by putting in your XL in place of resistance. Probably should take a picture of that, it's kind of messy. Okay. Let's look at transformers. It's a whole chapter in the text, but there's really not that much to it. So a transformer is nothing more, this is now chapter 14. A transformer is nothing more than two inductors close to each other. And what I'm going to pass around are some transformers.
Oh, maybe, I don't know if you want to.
No. Sure, it's good. This gets heavy.
pretty heavy.
Yeah, they are heavy. Pass that back to Royce then. Now, what you guys have is a conventional transformer. If you open that up, open those transformers up and take them apart and whatnot, you're going to see what is known as a three-legged core. The metal, the part that's heavy, the iron laminations, are actually the shape of that shape actually when you open that up. And the windings for that transformer, the transformers are nothing more than two inductors that are in close proximity to one another. So in this case, you're going to have windings around this center part here. Like so. And that's going to be one, that might be the secondary. And then you're going to have another set of windings right on top of those. And that's called the primary. I'm only showing a few windings. Those transformers that you have there probably have hundreds of turns on them. And this is called a three-legged core. So remember, when you have wire that's in the shape of a coil, you actually have a north and a south pole created. And so in this case, the core concentrates that magnetic field to that area. It's called a three-legged core. It's possible that you could have a transformer, they're not quite as efficient. Same thing, but you could have your windings out here. Like so. And the magnetic field would kind of be like this, and then you'd have some out here in the air, like that. So these guys are not quite as efficient. I actually don't think I've ever seen a transformer wound like that, but that it could be done. And then they have what is known as five-legged cores. Where your windings are here. One, two, three, four, five, yep. And here's the primary. And here's your magnetic fields like so. You would use something like that for a high power transformer. A utility might use a five-legged core when they're building a transformer to power up a development. These guys, typically the ones that I passed around, the bigger ones are for a power supply. Some power supplies that went belly up here, and I just took the whole thing apart and saved the transformer. And then the little guy transformers, the smaller ones that I passed around, I think there's two of them. That would be for like for a doorbell, system, ding dong, that kind of thing. So again, the smaller the core, the lower the power. Okay. Now, what's going on here with a transformer? Well, when you have a coil of wire like this, and you connect that to a power supply, as that magnetic field expands, what happens? It cuts across this coil here, which is not real efficient. I guess I would get some transfer of energy on that guy, but not a whole lot. Technically, this coil ought to be wound right on top of the other one. So as you feed this coil from a source, the magnetic lines of force would have cut across the other coil and induce a voltage in the other coil, which would induce a current in the other coil. If you have, the idea here is that if you have a lot of turns here and fewer turns here, if you have, let's say, 100 volts on the primary, and you have a 10-to-1 ratio, 100 turns, 10 turns, you're going to get 10 volts on the secondary. If you have 10 turns here and 1,000 turns here, you feed this with 10 volts, it's a 100-to-1 ratio, you're going to get 1,000 volts out, okay? It just depends on the turns ratio. So the turns ratio determines the relationship between voltage and current in the primary and the secondary. Now, you can't create power. You can never, this is not a device that'll allow you to get more, even though you have 10 volts and 100 volts here, you cannot create power because as the voltage is increasing, the current is decreasing. So you have power on the primary is equal to power on the secondary. Same power in is equal to power out. And what is power? It's voltage times current. So the voltage on the primary times the current on the primary is equal to the voltage on the secondary times the current on the secondary. And so let's just take and divide by the primary, and we have V secondary over V primary, and that is equal to I primary over I secondary. So as this one is increasing, the current is decreasing. If I have the voltage, if I start out with 10 volts here and I end up with 100 volts here, I might end up having 100 amps here and 10 amps here. It's the same ratio. As one goes up, the other one goes down. And that's why on your transformers, you'll see that the size of the leads might show up a little bit differently. Where's the transformer? Yeah, on this one they don't. Some of them they do, some they don't. Some just use a minimum wire size and that's it, primary and secondary. They're kind of over-designed. But that's one of the things you have to take into account. If you're increasing